E3. Sure? These are called leverages. Okay, this is what we call as 1 minus H11. Okay, this is a leverage. This tells you how much E1. What it says? What it says is E1, E2 and E3 all will have an impact on E hat 1. And what will determine the impact of E2 on E hat 1? What will determine the impact of E2 on E hat 1? This quantity, right? Now can you actually tell me what this quantity is? Covariance. If I had lots of samples, then this is really, so it says the impact of E2 on E hat 1 will depend upon 1, the volume of E2, how large E2 is, right? And what is the covariance of the first and the second observation relative to the total variance in X, right? Relative to the total variance in X. Okay. Now, if we assume that X1, X2 are all independent, if we assume that E1, E2, I mean X1, X2, E1, E2 are all independent of course. If E1, E2 are also, if X1, X2 are also independent, then obviously these covariances will not matter. This covariance will be 0. So effectively we will be concerned with this, right? This is the leverage, 1 minus H11. Okay, 1 minus H11, right? So we will roughly write E1 hat is equal to 1 minus H11 into E1, right? This I left opaque in the last class, right? I had not really told you what this is. Okay, now this motivates our, so we can now discuss the white heteroscedastic consistent errors a little bit more carefully. Okay, a simple approach, see, what is the problem? The problem is if there is heteroscedasticity, assume there is heteroscedasticity and no autocorrelation, right? Then variance of beta hat in our simple model is x1 square sigma 1 square plus x2 square sigma 2 square plus say xn square upon summation xi square whole square, right? Model without an intercept. Okay, if you have a model with an intercept, how does this change? This changes as follows. If you have a model with the intercept, this becomes x1 minus x bar square sigma 1 square, x2 minus x bar square sigma 2 square into xn minus x bar square whole square, right? That becomes the correct formula for the variance of beta hat. Okay, we understand all this. The point is, we do not know sigma 1 square, sigma 2 square, sigma n square, right? So one simple approach would be to replace sigma 1 square by E1 hat square, because what is E1 hat square? We want an estimate of sigma 1 square. We do not observe sigma 1 square. What we have is an estimate. We have E1 hat square. E1 hat square could be as an estimate of the variance of the first error term. So this becomes sigma 2 hat square. This becomes, so this becomes yeah, right? This is a very simple approach that one can take. So instead of sigma 1 square, the estimated variance of beta hat now is x1 minus x bar square, E1 hat square right? Plus x2 minus x bar square e2 hat square up to xn minus x bar square e hat n square upon summation xi minus x bar square whole square. Right? If you did that, then you would be doing what are called White's heteroscedastically consistent variance covariance matrices. In a matrix sense, what would happen? In a matrix sense, you know, okay, for a matrix formulation, you know that beta hat is equal to right? In a matrix sense, you know that beta is equal to x dash x inverse x dash y, right? Which is equal to x beta plus e, right? Which is equal to x dash e right? Okay? So variance of beta hat, yeah, this variance of beta hat minus beta transpose, this is how to square a matrix, x into x transpose, right, which gives you a n cross 1 into 1 cross n cross n, so all the cross products are there, right? Okay, this is what? This is expectation of, so what is this? X dash e into x dash e transpose. Okay. Which is what? Now this must be all child's play for you. You must all know this very well because we have done this so many times over, right? Which is what? Which is expectation of into e dash x dash x inverse, right?
Yes.
Which can be written as right? We are coming to the sandwich estimator that we talked about in the last class. Now what will the dimension of E dash? What is the dimension of E dash? N cross n, because E is n by 1, E dash is 1 by n, so E n cross n. So what do the diagonal elements tell you? The diagonal elements will tell you the variance of sigma 1 square, sigma 2 square, sigma 3 square, so forth, and the off diagonal elements will tell you the covariances. We are assuming that there is no autocorrelation, so the covariances are 0. Right? So the autocovariances are right. So we are assuming that the autocovariances are 0. Okay, right. So which means that E dash. So let's say that expectation of E dash